This is review time. Last chance to ask questions before the exam on Wednesday. So what do you think? What's giving you trouble?
Can you just go back over the pH, the thing with the exponent?
Yeah.
The way I learned it in high school was like the log of whatever equals.
Yes. So let's go back over pH. pH is the negative log of the hydronium ion concentration. That's the definition of it.
Okay.
But we know that logs return exponents. So if we have a log of some number like 10 to the third or 10 to the minus 3, that gives us minus 3. That's what log does. So if you want to know the pH given the hydronium concentration, you just do this, given the hydronium concentration. So the other thing then that you need to be able to do is look at the hydroxide concentration, realizing that they are related. So one thing that we said before was that the hydronium concentration, these brackets mean concentration. The hydronium concentration times the hydroxide concentration in an aqueous solution is always 1 times 10 to the minus 14. So that is the actual constant. But what's usually more useful about that is saying that the pH plus the pOH equals 14. It's another way of saying the same thing because the pOH is to the hydroxide concentration what the pH is to the hydronium concentration. If you take the log of two things multiplied together, that's the same as the log of each of them, the two logs added together. That's just a property of logarithms. So I think it's easier to remember the pH plus pOH equals 14 rather than mess with dividing big or really small exponents. So that's how we get all that stuff from before. So then going the other direction, if you're given let's try it. If I tell you that the pOH is 5, then you should be able to calculate the hydroxide concentration, the pH, and the hydronium concentration. So the hydroxide concentration, remember the pOH is the negative log of the hydroxide concentration. So if the pOH is 5, and 5 is the negative log of the hydroxide concentration has to be 10 to the minus 5 molar. So it's like the opposite of taking the log is raising something to a power of 10. Raising 10 to a power of the number. The pH we get by remembering this pH plus pOH equals 14 thing. So if the pOH is 5, the pH has to be 9. 9 plus 5 is 14. And then the hydronium concentration we get from the pH. Same way we got the hydroxide concentration. We raise it up on 10 with a negative sign. That's it. Feel like you're okay with that? Maybe, yes. If the numbers are not nicer than that, I mean, they will be on Wednesday, but if the numbers are not nicer than that, you need to put it in the calculator. And you would still do the same thing, but you put it in the calculator to actually get the numbers. But yeah, we only require 4 function calculators for this class, not log calculators, so you don't have to do that. It's not like an alarm or something. That's right.
So on the test, we'll have, let's say, page 9.
Yeah.
And we have to.
Right. Yeah. Right. So I'll keep the numbers even. All right, what else? What else is giving you trouble with this?
What else are you gonna have to like write out on the test?
I can tell you. Let's see. Let's take a look at the objectives. Where's the blackboard here? All right, so you should still know all the stuff from the first exam, right? Everybody still good with all that? I will tell you, like, I'm not going to pick out random stuff from the early chapters that's like really specific, but stuff like knowing, especially I think the naming, the equations, balancing equations, moles, that kind of stuff, because that all comes into what we are still doing. So whether it's writing formulas from names, if you need to review your polyatomic ions, make sure you do that. All that stuff will still be on this exam. The things you'll be writing, all right, so we talked a bit about energy. So you should be able to draw those energy diagrams for reactions, endothermic versus exothermic. What do the different things mean when we draw those curves? So that's a thing that you should be able to draw. Just ask about that. The main, probably the biggest chapter we've done since the last exam is talking about gases and liquids and solutions. So make sure that you can describe the different gas laws that we looked at in the lab with the balloons and stuff. Make sure you know those. The intermolecular forces was big. So what types of intermolecular forces, hydrogen bonding versus dispersion forces, how does that affect boiling points? That will probably be less drawing and working out problems and more like writing an explanation or just answering questions about what types of forces are in these, what types of forces are in these. The calculations in this exam will be primarily the pH thing that we just did, the molarity, mass percent, solution type concentrations, and those will be coupled together a little bit with equations too. So remember that we can figure out the number of moles of something from the solution, just like we did with just like we did earlier with grams, and so we can think about those as well. Maybe we should do an example of that. Because the other stuff we've just been talking about, so the acids and base stuff, and then drawing the structures, drawing isomers, figuring out if stuff is isomers or not. So we'll definitely do some of that. So where do you want to start? What do you think is going to be the most trouble? Because we're sort of just doing questions and review today, I wasn't going to take a formal break, but if you need a break, just step out whenever you need. What are we going to talk about? Should we try a molarity equation type problem? Okay. All right, so let's use this same acid-base question that we had in the quiz. And actually, I'll just leave that on the board, but I'm going to word it to be a little bit tougher of a question. So how many moles of sodium hydroxide? And remember on the exam, I may also just write the name rather than the formula, so you should be able to put that name down. Are needed to neutralize 55 milliliters of 0.15 molar phosphoric acid. All right, so in a question like this is not a specific line item on the objectives, but this is a combination of several. Because you need to be able to write a balanced neutralization reaction. You need to be able to solve for moles from molarity and do some mole ratios. So let's walk through it. First thing, always when you're talking about a chemical reaction, is to write down a balanced equation. We've got a balanced equation there, so I'll just copy it here so it's in the notes or for anybody watching on the internet. But you'd need to come up with this balanced equation for the neutralization of phosphoric acid and sodium hydroxide. All right, and we talked about that before. So when you get that keyword neutralize, or when you see that it's a base and an acid reacting together, then you know a product's going to be water, and the other product is the other pieces of those reactants. So the sodium and phosphate, and then it's up to you to make the correct compound, because you know that phosphate is a -3 anion. You know you need 3 + 1 sodiums to pair with it. If things like that are still giving you trouble, please go back and review that from however many chapters ago, because that kind of thing is going to keep coming up every single time. So make sure you know those polyatomic ions and you know how to build those compounds. All right, so now we've got an equation, and the question is asking about moles. So this is very similar to the types of questions we got back in chapter 4 or 5, where it would say, okay, if you have 3 moles of this one, how many moles of this other one do you need? And you put it in that mole ratio and you solve from there. The difference here is, instead of just being given an amount of moles of one of them, we're given a volume and a concentration. So that's a little bit different. So we want to solve for the number of moles of this, but we haven't actually been given exactly the other one. We've just been given enough information to find it. So we have to remember that molarity equals moles per liter. So how many moles in a liter? So if the molarity is 0.15 molar, that means there are 0.15 moles of whatever the solute is in a liter of solution. That's that definition. Make sure you know those solution concentration definitions for when these kinds of things come up. So molarity is moles per liter. That means we've got 0.15 moles of phosphoric acid in every liter of solution. But we don't have a liter of solution. How much do we have? Yeah, we got 55 milliliters. So we can put that into liters and figure out the fraction of moles that we have there. So let's do that. So you got 55 milliliters. There are 1,000 milliliters in a liter. The milliliters cancel. And then our molarity tells us that there are 0.15 moles per liter. So liters cancel and we end up with moles. So doing that calculation, we get 55 divided by 1,000 times 0.15, 0.00825. And let's make sure to keep track of our units. So that's now moles of phosphoric acid. The volume multiplied by the molarity, moles per liter, cancels the liters and gives you moles. So that's how you can tell how many moles you have if you have a particular volume and a particular concentration of solution. So now we know that we have 0.00825 moles of this one. And if we've got 0.00825 moles of that one, we can figure out from the mole ratio how much of the other one we need. So that looks like this. So we want to find the mole ratio of phosphoric acid versus sodium hydroxide. We get those numbers from the equation, 3 to 1. So we need 0.02475 moles of sodium hydroxide. All right, so let's think about what we did. We got the balanced equation. We figured out the number of moles of one by multiplying the concentration and the volume. And then we used the mole ratio just like back in chapter 4 to figure out how many moles we need to deal with. So that's an example of how some of the new stuff, the solution stuff, gets mixed with some of the old stuff we've done already on the exam. And that's why I say the exams are cumulative. It's not because I'm pulling out random stuff from old chapters. It's because you need all that stuff put together to be able to solve these kinds of problems. All right. What else? The mass percent? Yeah. So with the percent, the mass percent ones, we don't usually deal with chemical equations with that because it doesn't make sense. If you're going to use moles, just use molarity. But we do need to know how to make those types of solutions. So let's say what is the mass percent, which is percent m over m. Of a solution made from 5.3 grams of sodium chloride and 106.4 grams of water. Do you want to try it first? No. Let's do it together. Just thought I'd ask. So we have to remember here again the formulas. The key to all these solutions things is remembering what the definition is. So molarity is moles per liter. What's mass percent? How do we define mass percent? Well, no, it's all mass. It's all mass. So mass percent, you can go back in the notes and check this. It's the mass of the solute, the thing going in, solid thing usually, doesn't have to be solid, but over the mass of the whole solution and then put into a percentage. So in this case, that is 5.3 grams of our solute NaCl. And then the solution is everything together. So that's the solvent, which is water, and the solute together. So 106.4, and then we have to add 5.3, which is 111.7. So we get 0.0474, which would be, 4.74% by mass. So it's a simple percentage. How much of a percent of the overall solution is the solute? There were some mass by volume percents on the lab also, but you'll notice that is not in the objective, so you won't have to do that calculation for the exam. All right, what else?
How about redox reactions and elements that are changing charges? Can we practice this?
Yeah. So I'll write down a couple reactions, and you tell me if these are redox reactions or not. There's one, and I'll use the second one as our same reaction that we've been talking about. All right, are either of these, both of these, none of these redox reactions? What does that mean, and how do you know? What do you think? It's okay, you can just guess. The first one is or is not? Is, okay. Agree, disagree?
Hydrogens.
No, but that's not what the question is. Is it a redox reaction or not? So, any other comments? Agree? Yeah. What do you look for here? What's the definition of a redox reaction? Yeah, reactions where things are changing charges. So where the charges change throughout the course of the reaction, meaning from the left to the right. So sometimes that's easy to spot, and sometimes it isn't. In these reactions, I would say, well, in the first one, it's not necessarily obvious what changes charge and how it changes charge, but there is a key to knowing that these are redox reactions, and that's that they have pure elements on one side or the other. Anytime there's a pure element in a reaction, that is evidence of redox because every pure element has a charge of 0, or not, which is all oxidation state of 0. So if it's pure, like the zinc, like the hydrogen, that has to be a redox reaction because something must have changed. Even if we don't know what the hydrogen's charge is in the left side of the reaction, we can say it definitely was something on the left side and then it became 0. So, same thing with zinc, although you could probably figure out that zinc on the right is a +2 because it's got 2 minus 1 CLs. So zinc has gone from 0 to +2. So actually that's the oxidation part and the hydrogen is the reduction part. You don't need to know that, but you can identify that that is redox. Anyway. So the bottom one is not because nothing changes charge there. You still have the same ions on both sides of the equation, the sodium and the phosphate. The hydrogen and the hydroxide have come together to form water, but that doesn't change their charges. That doesn't change their oxidation states, we'd say. So that's an example of not a redox reaction. Anything where, well, I don't know about anything, but most reactions where you have that kind of like switch partners behavior where the ions that work together kind of switch with the other ones, those are usually not redox. They're just switching around.
Can you notice if your element itself
Right.
is
It has to be, yeah.
Okay.
Because if it's by itself on one side,
It
that
has
means
to
it
be.
changed somehow. So it must have become an ion or was an ion. Whatever, yeah. So if you see a pure element, it has to be a redox. Yeah, question. Does that help? Yeah.
So you said we don't need to know like which part is the oxidation and which
Right.
part of
Right. I can confirm that on the things, but I believe that is true. Yeah. So you should know what oxidation reduction are. Identify oxidation reduction reactions. So you don't have to figure out which ones are oxidation and which ones are reduction.
Is there going to be a question where like you have to identify whether it's going to be an acid or a base?
Yeah. Yeah, let's see one of those. Like the acids and the conjugate acid and the base and that, yeah. All right, so in an acid-base reaction, we can determine the acid and the base, the conjugate acid, conjugate base. So let's look at one of those. Oops, that's not right. Hold on. Okay, so here's our reaction. So identify the acid and base on the left, conjugate acid and conjugate base on the right. All right, so what's the acid? Yep, the HNO3 is the acid. How do you know? Yep, it loses its hydrogen. So that's the acid. And once you've got one of these, you get all the other ones just because they all complement each other. So the other one on the same side is going to always be the base. So then on the other side of the equation, the conjugate base is the one that's similar to the acid. So this is going to be the conjugate base. And that makes this one the conjugate acid. We could also say that those are the acid, or the acid and the base going from right to left. Way of saying conjugate acid and base.
Drawing the energy diagrams
Yeah.
for reactions.
Okay. All right, so here's our axes. This is our reaction coordinate or reaction progress. And this is energy. So if I told you that a reaction, you mix some stuff in a test tube and it got hot to the touch, what does that tell you about the relative energies of this reaction? Is energy being released or is energy being absorbed? Released, right? If it feels hot, that means the energy is going out into your hand. So if energy is being released, what does that tell you about the relative positions of the starting and ending points? Is the ending point going to be lower in energy or higher in energy than the starting point? Think about what's happening. So if the thing is getting warm, that means that the energy is coming out of the molecules and into your hand or whatever, solution or yeah. So if the starting energy is here, have the reactants or the chemicals, have they lost energy or have they gained energy? They've lost energy because they've transferred it to the surroundings, to you. So that means that the end is going to be lower. So if it's exothermic, if the energy is coming out, that means that the products are going to be lower in energy than the reactants. So the only thing left is to draw the activation energy. Which is the little hump that it has to go over to get started. So then looking at this diagram, we can pick out a few key things. The overall energy of the reaction is the difference between the starting and ending point. So that's how much energy is released overall in the reaction. The activation energy is the amount of energy that needs to be put in to get the reaction started. That very top tip point is called the transition state. That's the highest energy that's like right when it's right in the middle of whatever the reaction is doing. Then you've got the reactants and the products.
How would this be worded? Would you graph?
Yeah, it could be whatever. Yeah, I could give you the graph and ask you for the stuff. I could ask you to draw the graph. I could say there could be like on the quiz there were some numbers on it, so you had to calculate the whatever energy by figuring out how high it went, how low it went, any of those sorts of things.
Can it be any of those? Do we have to like write out the? Can we do something?
Oh, so by the way, if you want more practice with this kind of stuff, we'll get some examples from this too. I put down here in the notes folder, or the course materials folder, I didn't think that our book did a great job of just having enough practice with drawing these types of structures. So I scanned in this chapter of a different book that has a lot more and like is a lot more just obvious about it and more descriptive about it, and they have a lot more practice. So let's try some of these. Let's see, scan a couple over here. All right, so draw line structures of those three molecules. So everybody try to draw these, and then what I'm going to ask you to do is when they're drawn, is look at the other people's around you, and they may not look the exact same, and that might be okay. So when you're looking at the other person's structures, try to figure out if they're actually the same or if somebody's wrong. Because depending on how you rotate your bonds, you may actually have drawn totally fine, something totally fine, even though it looks different. See you Wednesday. or less. You got all the structures yet? Maybe? All right, I'm going to draw them the way I would draw them, but that doesn't mean that you're wrong if yours look a little different. The important thing is that they're all connected in the same way. So if you have a question, let me know and I'll take a look at it. This first one, I would say, I would look across the middle and say, okay, it looks like about 5 carbons across the middle. So 1, 2, 3, 4, 5. Then there's 1 more coming off of the second from the left and 2 coming off the second from the right. Something like that. Yes, no, okay. This other one, there's a few different ways you could look at this. So technically the longest chain of carbons would be starting at the top and going like down and then over, because then you get 4. But you could also just see the 3 in the middle and go 1, 2, 3. And you could notice that this one has 2 more coming off of it. And this one has a double bond to oxygen. Like that. The one on the right is written vertically. This molecule is actually called glycerol. But we don't have to draw it that way. We can. So we could go put our 3 carbons like that. And then have 1 OH coming off the top, 1 coming off the middle, 1 coming off down there. You could also just tilt it and write it straight across. Over 2. Anybody have structures you're not sure if they're the same or not? Yeah.
So for the first one, I originally had this going this way. Would that make a difference?
This way.
There.
That's fine. Yeah. That's
So that was okay.
Usually we try to draw it to best approximate those 110-degree angles that are that tetrahedral geometry, so that's why we usually see it like that. But I would say as long as it's connected properly, it's correct. That may change a little when we get to carbohydrates and stuff that have a little more complicated structures, but for now, it's fine. Yeah. Let's look at some of these condensed structures and see how we draw them from the condensed structures. Let me pick some of these out. Let's do like this one. And maybe this one. Try those two. This one, the second one, has a little bit of a trick in those parentheses at the end. See if you can figure out what that means. All right, let's take a look at these two. So the first one's pretty straightforward except for the oxygen in there. Remember that oxygen doesn't get abbreviated, so you got to watch out for that and make sure to include it. So this one's got 3 carbons in a row, then the oxygen, then 1 more carbon. So make sure, one way, we haven't been doing this, but one way to check this that's always good is number everything. You can number the carbons, you can number everything, you can number whatever you want to make sure that you've actually got everything accounted for. So that way, like let's say you left off that last one. Let's say you just did it like this. Well, if you were numbering your carbons, you'd go, okay, 1, 2, 3, there's 4 carbons. 1, 2, 3, oh, I'm down a carbon. I got to add one. I have to add one. Let's see, it's on the other side of the oxygen. So I would add it there. So adding those numbers can help. right, for the next one, it's mostly okay, except when we get to the end. What does it mean when there's two CH3s, when it's CH3 parentheses 2? Yeah, there's two of them, but are they going to be in a row or not? Yeah, they have to kind of both be at the end, because if they were in a row, there would be too many bonds on one of those carbons. If it's a CH3, it has to be in the end, because carbon can only have 4 bonds. Let me show you what I mean. So let's write this out. And this is something you can do on the exam too if it's helpful. You can keep it condensed, but actually draw the bonds out to help you see everything. So we've got CH and then CH3, and we can't put another CH3 here because this one now would have 5 bonds. 1, 2, 3 hydrogens, and then 4, 5. So that doesn't work. So it has to come off of this carbon. Also, that carbon's missing a bond. Otherwise. And then we can draw the condensed structure or the line structure from there. So we've got 1, 2 carbons, then an oxygen. There's a double bond between those two. Then the oxygen, then another carbon, then another carbon, and then this one has 2 CH3s coming off of it. So something like that. Again, if you had it zigging and zagging in the other direction, that's fine, as long as everything's connected properly. And with the angles don't need to be perfect, but they should be clear enough that you know where the carbons are. If you flatten things out too much, or if you draw them kind of separate from each other, it can be hard to tell exactly where the carbons are. So as long as it's clear, it's fine. It doesn't have to look exactly like what I just drew. They're connected the same, and I can tell what's connected to what. All right, now do some more practice with isomers, like determining whether they're isomers or not. Try one of those. Okay. Maybe watching. All right, I'm going to draw a few structures, and you have to pick out the isomers. I'm not going to tell you how many there are or which ones are isomers of which. You got to try to figure it out. All right, well, I will tell you, I ended up drawing more than I thought, so I'll help you out a little bit. There are 2 sets of 3 isomers each. So of all those 7 structures, there is 1 structure that isn't an isomer of anything, and there are 3 that are all isomers of each other, and then there are another 3 that are all isomers of each other. So see if you can find the 2 groups of 3 that are all isomers within those groups. One thing you may want to start with is just writing the molecular formulas underneath them. Find them? So? All right, so one group is this one, and this one. Those are isomers. They're all C5H10. The other group is this one, and this one, which are all C5H12.
Can you just go over how to write I guess the whole stuff for the ones that are like chain?
What do you mean?
So like so I like working backwards, but the ones
Okay.
that are in diamond shape, I'm having a hard time writing out the extended formula, then to shrink it down.
These like the
Yeah.
closed up ring ones?
Yeah.
Yes. Okay. So the way I would do that, so let's like take this one for example. So you first have to figure out how many hydrogens are on each carbon. You can do that just with little marks, so we can see that there's 2 on each carbon here. If you wanted to extend that out then and write a more of a condensed structure, you can't put it in a single line, but you can do this. Okay, that's about the best you could probably do for that one. Is that what you're asking about?
Yeah, never mind. I was trying to make it into one line.
Okay, yeah. When it goes around like that, you can't really make it into one line.
Okay.
The way that this is done, we'll get into this next week, but the way this is usually done is they just say C5H 10 or C5H9 and then like connect it to something else, and you're just supposed to kind of assume that that's supposed to be in a ring. Yeah, there's not a great way to do that in a line. This last one that I didn't circle is C6H14. So that one is not related to any of the other ones. Different formula completely. All right, let's try one where we have 2 structures and we have to tell if they are the same, isomers, or unrelated, like on the quiz. But sometimes a little difficult. All right. So these two structures, are they same? Are they isomers, or are they not related? Are they totally different? All right, so what do you think? Same? How do you know? You're right. That's true, but isomers have the same number of carbons too. Getting closer. Yes, yep, we're almost there. So it's not enough to just look at the formulas, because like up here, the ones with the same formulas were isomers, not the same. So what is it about these two that makes them absolutely identical and not isomers? It's how they're connected. So not only do they have the same formula, but they're connected together. So if we were to number this one, or actually before we do that, one of the ways we've been looking at this is to look at that longest chain. So you kind of figure out how many carbons that is. 1, 2, 3, 4, 5, 6, 7. And then it's got these like 2 extra ones coming off the 4th and the 6th carbon, the way I've got it numbered. So we do this. Okay, same thing. 1, 2, 3, 4, 5, 6, 7. But now it looks like they're different because I've got those on the things coming off of the 4th and 2nd carbon instead of the 4th and 6th. So are they the same or are they different? It does, yeah, sure. Because if they're placed at different places, that's isomers. That means they're not the same. So one way that you can do this, if you see things like this on the exam or just in the future, is stretch them out. So we know there's a big 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. Let's write it more in the normal way that we would write it, where it's straight like that. And then we've got one coming off, one from the end, and then 2 more in from there. Let's do the same thing over here. 1, 2, 3, 4, 5, 6, 7. We've got one coming off the end, 2, 3, 4, and one over here. And so now that you see them like that, you can see they're actually, the way I've got them drawn here, they're mirror images. So if we number from the middle, 1, 2, 3, 4, 5, 6, 7. Then we've got those things coming off 2 and 4. 1, 2, 3, 4, 5, 6, 7, 2 and 4 again. So that we can see that they're actually the same, because all we'd have to do is take one of them, flip it over, and we'd have the exact same thing.
Calculating polarity, like solutions.
Calculating molarity solutions? Yeah, let's try one of those. All right, so 6.8 grams magnesium chloride is dissolved in 500 milliliters of solution. All right, give it a try first, and then we'll look at it together. All right, we're running out of time, so we should probably go through this. We have time for a couple more questions. Okay, I was looking around at papers. Looked like a lot of you have a good handle on this, so that's great. The key here, again, as we talked about before, is remembering the definitions. So if you want molarity, you have to remember that that is moles of solute divided by liters of solution. Once you know that, everything else is just converting the stuff that we've done before. That's the only new part, is remembering that it's moles divided by liters. So we don't have moles and liters, we have grams and milliliters, but we can do those conversions. 500 milliliters, you can convert to 0.5 liters by dividing by 1,000. And 6.8 grams, we can move that to moles, or we can convert that to moles through the molar mass, which is going to take a little bit more work. We first need to find the formula for magnesium chloride, which hopefully you got is MgCl2. Then we can add up the molar masses, so that's 24.3 for magnesium and 35.5 for chloride. So 95.3, and the units for that are grams per mole. So that's how many grams are in 1 mole of magnesium chloride. Then we can do the conversion. So 6.8 grams. Oops, that's not an M. Try it again. And we want to get rid of grams and instead have moles. So 95.3 grams per 1 mole. Grams cancel, and we end up with 6.8 divided by 95.3. 0.0713 moles of magnesium chloride. Okay, so now we've got moles, we've got liters, we can calculate molarity. 0.0713 moles of solute divided by 0.5 liters of solution. Is 0.143 molar. Sorry, it's in grade 4. 0.143 molar. Is that what you got? Pretty close? Something like it? Okay. All right, we got about 10 more minutes. What else? What else are you worried about? What? You can use your notes to study for the test. But while we're talking about studying, remember, just like the last exam, this exam, I mean, it'll have some definitions and stuff like suspensions and osmosis or whatever, but most of it will be working through problems like this, solving for something or drawing something. So make sure that when you're studying, you're not studying like you do for anatomy or something where you just look at your notes and try to remember it all. Studying for this class should be doing problems, going through the homework, going through it again if you've already done it, going through problems in the book you haven't done yet, or that you can pull up on the Connect in the extra practice or in the ebook, just trying to go through it. Because you can actually understand the stuff pretty well, but not be able to show that by actually using it to solve a problem. So make sure that you really are making yourself solve problems in the next couple of days and not just looking at your notes and trying to remember them. Do this kind of stuff. Yeah.
I have a question for the private organic chemistry. What does that mean?
We haven't gotten to that yet.
Okay.
So that's not on the exam. Yeah. So the exam cuts off after number 4. So not number 5 and on. We'll pick that up next week. Anything else? Last questions? You all good? Everybody's gonna improve their score by at least 10 this time, let's say. You can do it, right? Maybe 20, 30 for some people. Nobody's gonna go down though, everybody's gonna get a better score. Except for those of you who got it in the 90s. You can go down if you want, that's fine. Everybody else should go up.